Well, in today's quiz, we have to find current in the resistor when we have already solved for the charge on the capacitor. We've done it yesterday, and I gave you actually a hint yesterday how to do it in a very straightforward way. Because when we were solving the equations, we recognized that the current flowing in the resistor is equal to the rate at which charge on the capacitor varies. So what we have to do is just to differentiate this equation with respect to time, because this is what a derivative is. So let's take a look at that. Now here we have two functions, sum of two functions. Over here we have a product of a function and a constant, and on top of it over here we have a composite function. So this is how this entire function looks like. All right, so now if we take a look at the sum, derivative of a sum of two functions is equal to sum of derivatives. So first we have to differentiate this function. And remember that we are although electromotive force is a function of time, it is a relatively simple function of time. So we are considering only in intervals when electromotive force is constant. So really this function is a constant. Capacitance is a constant, and electromotive force is a constant. The only points where electromotive force is not constant are the beginning of those periods. So derivative of a constant is 0. So the first term becomes 0. Now here I have constant times a function, so derivative of this product is constant times derivative of the other function. So I just copy the constant and calculate derivative of this exponential function. It's a composite though. So external function is the exponential function, and derivative of exponential function is an exponential function. So I will write down, I'll just copy it. 1 over resistance of the resistor, capacitance of the capacitor times the time which passed from the beginning of the interval. Now I have to multiply it by the derivative of the internal function. An internal function is a linear function, so it's just this coefficient here, minus 1 over RC. Okay, I can now, well, let's simplify this expression. So I have here Q over, actually how about since I have minus here and minus here, I will flip the terms. So capacitance and capacitance here cancel, so I will have electromotive force divided by resistance minus, now initial charge divided by capacitance of the capacitor gives me initial voltage across the capacitor divided by resistance, and then I have this exponential function. Why don't we now try to draw this function on top of the function which we had yesterday? And that actually yesterday, with the, I think that we assumed that resistance of the resistor was 1 kilo ohm, and capacitance was 1 millifarad. And this was toggling between 0 and 1. So it was 0 and 1 volts. So if these were 10 seconds over here, we saw the plot for the voltage across the capacitor to be like that. It was an exponential function. All right. Yeah, let's think first about what kind of current flows in the in the resistor. So let's start with this instant over here. What kind of current will flow at this instant? So at this instant, initial voltage on the capacitor is 0, correct. So this term is 0. Then we have here, well, 1 volt over 1 kilo ohm, so it will be 1 milliampere, e to the power, and t minus t0 is 0, so this is 1, right? So we will have 1 milliampere. How about if I mark it as a 1 milliampere? So at instant 0, current is going to be 1 milliampere. Let's see what will happen after 1 second. Well, this factor doesn't change, but over here we will have 1 second over 1 second. So it is e to negative 1, which means that what will happen with the current? Now recall that e is approximately 3. So here we will have 3 to minus 1. 3 to minus 1 is 1/3, which means that the current after 1 second drops to its 1/3 value. So after 1 second it will have this value. Now how about after 2 seconds? After 2 seconds we will have e to negative 2. So it will drop to 1/9. It's like that. And if I continue, I can see that current asymptotically approaches 0 value. Now, let's see what happens at this instant. So at this instant over here, for this interval, so initial voltage on the capacitor at this instant is going to be well, in this time interval, capacitor got charged. Yeah, this curve over here represented voltage across the capacitor, right? So it means that capacitor is already charged, and the voltage across the capacitor is indeed 1 volt. So this is 1 volt. What happened with the electromotive force in that next interval? What is the value of the electromotive force? 0 volts, correct. So we have 0 over here, we have 1 over here, and 1 kilo ohm, which means that it is this factor over here is minus 1 milliampere. Now let's see what happens at instant 10 seconds. So now this Ti is 10 seconds. So 10 seconds minus 10 seconds, we have e to 0. E to 0 is 1. So what is the value of the current? Not 1, negative 1. Correct. We got value of the current to be negative 1. So it drops to here. And then what happens as time passes by? What will happen at 11th second? We will have T minus Ti will be 1 second. So here we will have e to negative 1. So it will be about 1/3, right? 1/3. So the current, well, this time, well, drops, kind of drops. I mean, it assumes 1/3 of its previous value. So it drops to here. And then after 2 seconds, it drops to 1/9. And we can see that it asymptotically approaches value 0. And now the process repeats itself. Right now we have again voltage across the capacitor to be 0. Electromotive force jumps to 1 volt, and current is going to jump to 1 milliampere and asymptotically approach value 0. All right. Now, this was actually not the only way to find the current. I'm not going to do it now, but I will kind of show you a hint about it. Because let's find out what is the potential difference across the resistor. What is the potential difference across the resistor? Yeah, and let's take it that it's a potential difference between this point and this point. So we are consistent with our drawing. Always be consistent with your drawing. So how to find that? What do I have to do now? Well, I have already found. What did I find here? This is current. I mean, here I have charge. I mean, be more specific. What charge do I have here? This is charge on the capacitor. Which current is here? This is current in the resistor. Actually, this is current in every element because elements are connected in series. But the question was to find the current in the resistor. So I found current in the resistor. I know current in the resistor at an arbitrary instant. I know resistance of the resistor. So how can I find potential difference across the resistor? Ohm's law. We have to use Ohm's law. Just multiply this current by resistance of the resistor. And I will get potential difference. Well, if I multiply this expression by resistance, I will get rid of this resistance in the denominator, right? So answer is going to be epsilon minus initial voltage across the capacitor times e to negative 1 over resistance times capacitance and difference in time between the time of interest and the initial time. Well, so if I wanted to draw this function, how it is going to look like? Well, it's going to be proportional to that blue line, because that blue line represented current. Now I have to multiply this blue line by resistance, and it happened that I picked resistance to be 1 kilo ohm, which means that I have to multiply this by 1 kilo ohm. So now at this point, well, recall that this was 1 milliampere. So what would be the voltage across the resistor when that current was 1 milliampere? I mean, over here, actually, let me make sure that we, what do we have? I simultaneously make a plot of voltage over here. And that one is in volts. And current. And this one is in milliamperes. So how about voltage across the resistor? So when current is 1 milliampere, I have to multiply by 1 kilo ohm, right? Right, so I'm getting 1 volt. So it will overlap over here. Why don't you actually consult with each other for a while? What do we have on this drawing? Yeah, so I want really, because it's just a simple rocket science. It's really easy to comprehend if you concentrate at least once and analyze it. You'll think, well, really, it is simple. So talk to each other to make sure that your neighbor understands both plots. This plot, how about if I make it in red? So that plot in red is voltage across the capacitor. red is voltage across the capacitor, blue is voltage across the resistor. Is it clear now? Who understands it?
Is it?
Yes, Lee.
So the blue line represents the current?
No. Blue, well, yes. When we were making the plot, it was the answer is yes. Now, when the blue one is the current in that circuit, it's current in the source of electromotive force, in the resistor, and in the capacitor. All elements are connected in series. But if you read that blue line as current, you have to look that the vertical axis is current in milliamperes, because this curve is simultaneously voltage across the resistor. However, you have to look at volts now, because I selected resistance to be 1 kilo ohm. So when we multiply by 1, we get 1,000 times higher value. So this curve is simultaneously, and very good. I'm glad that you understand it. It's simultaneously plot of current and voltage, because they are proportional in a resistor, not off across. Voltage across the resistor is potential difference between this point and this point. This is voltage across the resistor, potential difference between these 2 points. Now let's take a look about red line. What do you understand? How do you interpret red line? What is the red line? Not off. Voltage across the capacitor, correct. It's potential difference between the top plate and the bottom plate. It is simultaneously some other quantity. Which one? If I change the scale, I would have to put another symbol over here, and that red line will represent that other quantity, because it happens that voltage across the capacitor is proportional to that quantity. What quantity am I talking about? Charge, correct. So at the same time, this one would be a charge across the capacitor. And we were thinking about, why do I have, no, millifarad. Yes, capacitance was 1 millifarad. So, for example, when the voltage across the capacitor is 1 volt, charge on the capacitor is 1 millifarad. All right. If we look at this, how we could solve, the second way of solving answering the question on the quiz would be instead of differentiation of the charge function and finding current, we could find potential difference across the resistor. Because I want you to take a look at these two and try to imagine what will happen if I add these two functions, the blue and red function. No, if I add over here in this interval, the sum is going to be 1. In this interval, the sum is going to be 0, and then 1 again. So we see that these two functions add up to the function representing electromotive force. And so in principle, I could solve a problem in such a way that I could divide this function by capacitance. This gives me potential difference across the capacitor, and then from the function representing electromotive force in the circuit, I can subtract the potential difference across the capacitor and get what? Not electromotive force. If from electromotive force I subtract potential difference across the capacitor, what am I going to get? A what? No. Definitely not current, because the answer will be in volts. Yeah, electromotive force is measured in volts, and voltage across the capacitor is measured in volts. Well, think about what actually electromotive force is. Yes, potential. I mean, particularly that I consider here, that this is an ideal source of electromotive force. So really, this electromotive force is potential difference between this point and this point. Right? I can actually even think that it's potential difference between this point and this point. Now let's call this as 1 V2. So this electromotive force is V1 minus V2. Now, what the red line represents? Voltage. Voltage across the capacitor. Well, so that red line is V3 minus V2. Now see what will happen if I subtract those two. So electromotive force minus voltage across the capacitor. So it will give me V1 minus V2 minus V2, so it's 0, minus V3. And what is that? V1. V1 minus V3. What's that? It's what? Voltage across the resistor. Right, we got, this represents voltage across the resistor. Right? Voltage between these 2 points. And current flowing here is proportional to this voltage. So this was the an alternative way of finding that current. All right. And now I promise that I will prepare the appropriate circuit. So I build a circuit. I mean, over here you can see the circuit. You use the same board in your lab. So if you have spare time during the lab, you can fool around with that. Do it. Yeah, and try to build other circuits. You can even build an amplifier in this. All right. So I connected this circuit. How about first I will disconnect these so we are not confused. I connected this circuit to the power supply, and here is resistor, and here is capacitor. So this is the source of electromotive force. It's a power supply. It produces potential difference, and actually from this computer I can select what kind of wave function I want for that voltage to be. So this power supply controls voltage between these 2 points, and I will use the one which we have over here as well. So sometimes the capacitor is being charged, sometimes it's discharged. All right. Now I'll turn on. Where do I have it? Aha! We need now the screen. So on the screen, you will actually see. I will simulate an oscilloscope on the screen, and we will see the plots of whatever we want to see. And right now, actually it's not working at this moment, but I can turn it on. All right. So this. Why I don't see all of it? Let's stop it.
You have to connect the measurement lead.
No. What I'm saying is the screen. I don't see it. Wait, because right now I see entire identical screen. So this is okay. Okay. Oh, I see. All right. So this section over here allows me to control the voltage. Right now, I ask the power supply to provide a positive square wave, I know. Okay, so the red line represents that square wave, and over here, how about if I turn it on so that it's live? Right now, the setting is such that one division over here corresponds to 1 volt. So what potential difference is applied to the to this? I mean, it toggles between what values? 0 and 5. Yes, so potential difference. So it's not like in the problem which I solved between 0 and 1, but between 0 and 5. I can change actually to 1 by flipping this one, but it works better when the voltages are somewhat higher. All right, now VB is the voltage. I mean, this second symbol represents voltage between these two terminals. Right now they are not connected to anything, so we have that 0, although I am able to pick up some signals, so in my body voltages are created. You can see that that green line moves when I do something. When I connect these two leads together, then we get a nice 0. Otherwise, there are fluctuations of potentials in my hands. All right, so now I connect these two terminals across the capacitor. And this gives me a potential difference across the capacitor. Now, how about if I try now to connect a second sensor to measure potential difference across the resistor simultaneously. So let me stop this one. Now I have to add one more sensor, and I want to add another voltmeter. Okay, I will plot this voltage, this third voltage also. And now start. Yeah, and the computer already is confused. Oh, no, I know. I hate computers. All right. Yeah, so the blue line, and now it picks up potential difference across my fingers on my body. And now I'm connecting this to the resistor. Ta-da! Aren't we happy now? Why? Actually, do you see what we've done? I mean, you haven't seen it before. And just by analyzing equations, we predicted the future. We predicted what will happen if we assemble the circuit that way. Yeah, so everything agrees perfectly. Now, this perfectly is not that perfect, though. There are various problems because we have to recognize that we never have ideal elements. Actually, I selected such values for potential differences and for frequencies that this circuit behaves indeed like a circuit which contains a separate capacitor, separate resistor, and the source of electromotive force. I really assumed, I mean, this works now properly, like we have ideal wires in the circuit. But now, how about if I wanted, actually, since I have this setup, I also wanted to show you how various elements behave. So how about if I close this one? And now I will disassemble the circuit. I will leave just power supply and connect capacitor directly to the power supply without a resistor. And relate potential difference across this element with the current flowing in this element. And how about if I even change the, let's say then I will take a sinusoidal wave. Well, how about if I start with a resistor? I want now to recognize that we have indeed that this is indeed a resistor. Yes, I connected an element, and do I see that this element is a resistor? Again, the red line represents voltage across the element. Green line represents current across the element. It's time dependent, so I vary both. And let's now play with some other waveform. So I put sine wave. Now let's have a square wave. How about if I change to triangular wave? Ramp up. Do we see? Can you see from those plots which you saw that the element which we are looking at is a resistor? How do you see that? Very good. Voltage and current are always proportional. Yeah, this makes it a resistor. In a resistor, voltage and current are always proportional. All right, now how about if I put indeed a capacitor over here? What can you see now? Do you see proportionality? Let's change. I mean, do you see the plot, by the way? I mean, this is over here. I mean, I can show you that there is a very small positive value here. Now current drops to a and a very negative value, and quickly comes back to a constant value, and drops and comes back to a constant value. Now how about if I change the waveform? Which waveform do you want to have? You pick one, just for your curiosity. Let's pick up sine. See if it makes sense. Are they, first of all, are they proportional? They are not proportional. How about if I change capacitance of the capacitor so it's smoother? But we saw a certain relationship between potential difference across the capacitor and current flowing through the capacitor. What was the relationship? If I have a capacitor and here I have current I, well, we figured out that this current is equal to what? Rate of change of the charge on the capacitor, correct? So it is dq over dt. We have to take derivative of charge. Now, charge across the capacitor is related to voltage across the capacitor. How? Charge on the capacitor is equal to capacitance of the capacitor multiplied by the voltage across the capacitor. So now if I substitute, how about if I do it? Capacitance times voltage. So I can take capacitance is a constant, and I will have that the current through the capacitor is proportional to the derivative of the voltage across the capacitor. Check that. Does it agree? Yeah, let's take a look. Find voltage is the red line. Find the points, a point when the derivative has a zero value. I will be going through various instances, and you will say yes or no. So is derivative of voltage here 0? No. Here? No. Here? Yes. Let's take a look at the current at this instant. Well, current at this instant has this value. Now over here, look at that. What is the derivative of voltage? Is positive, negative, or 0? Positive. And current is positive. Now here we have 0. Now derivative is positive or negative? Negative. And we got a negative value. Now tell me where is the point that the derivative, well, that the function has the highest slope, which means that the derivative has the highest value. Let's start from this point. Over here? 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 Yes. Over here the slope is the highest. And look that the current has the highest value too. So we see indeed that the current is proportional to the derivative of the voltage, which means that this is not a resistor. They are not proportional, and indeed it agrees with a capacitor. How about if we take a look at a light bulb? Oh no, I wanted to do one more thing. How about if I now put a square wave on this across a square wave. Now take a look. Is still current proportional to the derivative? Yes, right? I mean, we see that, like over here, when over here derivative is 0, current is approximately 0. Let me change it. Yeah, current here is approximately 0. Now this one, what's the derivative over here? Well, it's high. I mean, in principle, if it were really square, then we would have that derivative to be infinite. Yes, so current jumps to an infinite value. And now derivative is constant. We see that sorry, the derivative is constant, derivative is 0, so current drops to 0. Now see what will happen if I change the frequency though. So right now it's 10 Hertz. And I will now, it's 60 Hertz now. So I will stretch this plot a little bit. Oh, let's decrease that voltage a little. Let's make it even more. All right, so I made much smaller potential difference, but does it resemble something else? Look over here, derivative is, I mean at this point, derivative here, derivative of voltage looks like 0. The potential difference applied to that board over there is almost 1 volt. And remains constant. However, current varies. What's the conclusion? Do you recognize what kind of circuit has such a plot between current and voltage? Which one? Louder. I heard the right answer. It's an RC circuit. It's an RC circuit. It behaves like a circuit which contains capacitor and resistor. Where is the resistor? The what? Well, I mean, let's assume that power supply actually, because this is compared to this, it's still pretty good. This is a resistor. I was connecting capacitor through a resistor. We use resistors to connect things. Yeah, wire is a resistor. Remember about this also. All right, so thank you for your attention, and this will be all for today.